Venus. It is one of our closest planetary neighbors in the vast cosmic neighborhood. You have probably seen it. It shines brightly in our sky, often as the morning star or the evening star. This celestial body has captivated human curiosity for centuries, a brilliant point of light heralding the dawn or dusk. Its proximity to Earth and its similar size once led scientists to imagine it as a potential twin to our own world, perhaps even a lush paradise. However, as we have learned more, Venus has revealed itself to be a place of extreme conditions, a world vastly different from our own gentle Earth, holding its secrets tightly. The idea of Venus as Earth's twin is understandable when we look at basic numbers. Its diameter is about 95% of Earth's, and its mass is about 81% of ours. These similarities are quite striking in the solar system. Because of this, for a long time, people imagined a world much like our own. They thought perhaps it had jungles, oceans, and maybe even life. Science fiction writers often depicted Venus as a steamy, swampy world, but the reality, as unveiled by science, is far more dramatic and far less hospitable to life as we know it. The dream of a sister Earth was soon to be replaced by a more complex and fascinating truth. Venus is perpetually shrouded in a thick, unbroken layer of clouds. These clouds are not made of water like Earth's. Instead, they are composed primarily of sulfuric acid. This dense blanket completely hides the planet's surface from our direct view with visible light telescopes. This opacity is what maintained its mysterious allure for so long. What secrets lay hidden beneath that impenetrable veil? What kind of landscape could exist under such conditions? It took the advent of radar technology and robotic space probes to finally begin to peel back these layers of mystery and give us our first glimpses of the Venusian surface. Understanding Venus is not just about satisfying our curiosity for a neighboring world, it is much more profound than that. By studying Venus, we learn about how planets form and evolve. We can investigate why a planet so similar to Earth in size and composition took such a drastically different environmental path. It offers us a stark comparison, a natural laboratory to understand planetary atmospheres, greenhouse effects, and the delicate balance that makes a world habitable. The lessons from Venus resonate deeply, especially as we consider the future of our own planet's climate and our search for life elsewhere in the universe. When we talk about the physical characteristics of Venus, we start with its size. As mentioned, it is remarkably similar to Earth. If Earth were a basketball, Venus would be just slightly smaller, perhaps like a volleyball. This makes it a terrestrial planet, meaning it is a rocky body, not a gas giant like Jupiter or Saturn. It has a solid surface you could, in theory, stand on, if you could survive the other conditions, of course. This fundamental similarity in size and bulk composition is what makes its profound differences so very intriguing to planetary scientists across the globe. The composition of Venus is also thought to be quite similar to Earth's. Scientists believe it has a metallic iron core, a rocky mantle, and a silicate crust. These are the same basic layers that make up our homeworld. We infer this structure based on its density and by observing how spacecraft are affected by its gravity. However, unlike Earth, Venus does not appear to have active plate tectonics. Earth's crust is broken into plates that move around, causing earthquakes and forming mountain ranges. Venus's crust seems to be more of a single, continuous shell, though it shows evidence of past volcanic activity. The surface of Venus, hidden beneath its dense clouds, is a landscape of intense geological features. Radar mapping by spacecraft has revealed vast plains, extensive highlands, and thousands of volcanoes. Some of these volcanoes are enormous shield volcanoes similar to those found in Hawaii, but often much larger. There are also unique circular dome-like features called coronae, which are thought to be formed by upwellings of hot material from the planet's interior. Impact craters are present, but fewer than on Mercury or the Moon, suggesting the surface is relatively young, perhaps resurfaced by volcanic activity a few 100 million years ago. One very interesting aspect of Venus is its rotation. It spins incredibly slowly on its axis, taking about 243 Earth days to complete one rotation. This is longer than its year, which is about 225 Earth days, so a Venusian day is longer than its year. Furthermore, it rotates backwards compared to most other planets in the solar system, a phenomenon known as retrograde rotation. Venus also lacks a significant global magnetic field, unlike Earth. Our magnetic field protects us from harmful solar radiation. The absence of one on Venus likely has profound effects on its atmospheric evolution and interaction with the solar wind. The atmosphere of Venus is perhaps its most defining and terrifying feature. It is incredibly dense, exerting a surface pressure more than 90 times that of Earth's. This is equivalent to the pressure you would experience nearly a kilometer deep in Earth's oceans. Imagine trying to walk around with that much weight pressing down on you from all directions. The sheer density of the air itself would feel like moving through a thick fluid. This immense pressure is primarily due to the composition of the atmosphere, which is about 96.5% carbon dioxide, a potent greenhouse gas. Above this crushing atmosphere hang the infamous clouds of Venus. These are not fluffy white water clouds like we see on Earth. Instead, they are thick global layers made of droplets of sulfuric acid. These clouds are highly reflective, which is why Venus appears so bright in our sky. They reflect about 75% of the sunlight that strikes them. While they reflect much light, they also play a crucial role in trapping heat beneath them. These clouds extend from about 45 to 70 kilometers above the surface, and within these layers, conditions are incredibly corrosive, posing a huge challenge for any probe attempting to study them. This combination of a dense carbon dioxide atmosphere and thick cloud cover leads to an extreme version of the greenhouse effect, often called a runaway greenhouse effect. Sunlight that does penetrate the clouds and reach the surface is absorbed and then re-radiated as heat. However, the carbon dioxide and other greenhouse gases in the atmosphere trap this heat, preventing it from escaping back into space. This has resulted in surface temperatures on Venus averaging around 465 degrees Celsius or 870 degrees Fahrenheit. This is hotter than the surface of Mercury, even though Mercury is much closer to the Sun. It is hot enough to melt lead. The weather on Venus is, as you might expect, quite extreme. While the surface winds are relatively slow, perhaps only a few kilometers per hour, the upper atmosphere is a different story. At the cloud tops, winds can reach speeds of over 360 kilometers per hour, about 225 miles per hour, circling the planet in just 4 Earth days in a phenomenon known as superrotation. There is also evidence of lightning within the Venusian clouds, much more frequent than on Earth. And while it might rain sulfuric acid in the upper atmosphere, this acid rain evaporates long before it ever reaches the scorching hot surface below. Humanity's quest to understand Venus has led to numerous robotic emissaries sent to brave its harsh environment. The very first successful interplanetary mission by any country was NASA's Mariner 2, which flew past Venus in 1962. This pioneering probe confirmed the incredibly high surface temperatures that ground-based radio observations had suggested. It was a pivotal moment, shattering the dream of a habitable Earth like Venus and revealing a far more alien world. Subsequent flyby missions from both the US and the Soviet Union continued to gather data about its atmosphere and magnetic field, painting an increasingly detailed, albeit daunting, picture. The Soviet Union, in particular, made Venus a primary focus of its space exploration program. Their Venera series of spacecraft achieved remarkable feats. Venera 7 in 1970 became the first spacecraft to successfully land on another planet and transmit data back to Earth. It survived for 23 minutes in the crushing heat and pressure. Later, Venera missions like Venera 9 and 10 sent back the first images from the Venusian surface, revealing a rocky, desolate landscape. Venera 13 and 14 even managed to drill into the surface and analyze soil samples, providing direct evidence of its basaltic composition. These missions were triumphs of engineering. While landers provided ground truth, orbiters gave us the bigger picture. NASA's Magellan spacecraft, which arrived at Venus in 1990, was a game-changer. Using powerful radar, Magellan was able to pierce through the thick cloud cover and map over 98% of the planet's surface in high resolution. These radar images revealed a world shaped by extensive volcanism, with vast lava plains, towering shield volcanoes, and peculiar dome-like structures called coronae. Magellan's data provided a global geological context for Venus, showing no signs of Earth-like plate tectonics but plenty of evidence for a dynamic, geologically active past and possibly present. Studying Venus teaches us profound lessons about planetary science. It serves as a stark warning about the potential for runaway greenhouse effects. highlighting the delicate balance that maintains Earth's habitability. Understanding why Venus, so similar in origin to Earth, evolved so differently is crucial for comprehending the conditions necessary for life to arise and thrive. Future missions are planned by various space agencies aiming to delve deeper into its atmospheric dynamics, geology, and the tantalizing question of whether Venus might have once been more hospitable. Each new piece of data helps us understand not just Venus, but our own Earth and our place in the cosmos.